with the session?
Sure, madam. Please go
Okay,
ahead.
sir. Yes. Very good afternoon to all. I, Dr. Neelam Chaplut, welcome all participants in the fifth, that is last session of the Faculty Development Program, Trends and Application in Machine Learning and Deep Learning, organized by Computer Science Department of Purnima College of Engineering, sponsored by Rajasthan Technical University under TechUp 3. I welcome Dr. Nitin Khanna, Assistant Professor, IIT Gandhinagar, with us for the session. I also welcome Dr. Surendra Yadav, Head of the Department, Computer Science Department, for the session. I welcome Vipin Prakash Yadav, Event Coordinator, RTU, Dr. Praveen Gupta, a Professor, Purnima College of Engineering. It gives me immense pleasure to welcome Dr. Nitin Khanna sir for the session. He is a well-known person for his quality research and knowledge. We are privileged to have him over here, and we are thankful to him to agree upon to spare some time from his busy schedule to deliver this expert talk. So wishing you a very happy Teachers' Day, and the topic which sir is going to take is learning and deep learning, machine learning and deep learning for multimedia forensic in seeing, still believing. I would like to give a brief introduction of sir. Dr. Nitin Khanna sir received the BTech degree in electrical engineering from Indian Institute of Technology, IIT Delhi, in 2005. He received his PhD degree in electrical and computer engineering from Purdue University, West Lafayette in USA in 2009. From 2009 to 2012, he was a postdoctoral research associate with Video and Image Processing Laboratory, School of Electrical and Computer Engineering, Purdue University. He is currently an assistant professor with Electrical Engineering, Indian Institute of Technology, IIT Gandhinagar. His current research interests include the broad field of signal image and video processing, particularly multimedia security, signal processing for healthcare, and low complexity imaging. He has extensively published in various international conferences of repute and leading SCI and Scopus Index journals for his research areas. Without taking much of your time, I'm quite sure you all must be eagerly waiting to hear the sir. So I hand over the session to Dr. Nitin Khanna sir for the technical session, for the expert talk.
Thank you very much, madam. Thank you everyone for joining. Thanks a lot for the organizers for conducting this session, which will of course enhance the learning of not only the audience, but as well as the speaker, I guess, because the more we interact with people who are interested in a field, the more we gain knowledge by exchanges of ideas. So there was a number of wonderful sessions all of you have already participated in. I would like the session to be more of an interactive session rather than just monologue. So feel free to type in your questions in the chat, and in between, once I cover a concept, I'll look back at it and try to address those questions so that we go in a phase by phase manner rather than completing the whole 1.5 hour presentation at once. Uh, uh, just to make sure, let me first share the slide. Host has to enable the slide screen sharing, madam.
I think you will be able to share the screen. Are you not able to do that?
No, it's saying host disabled for.
Okay, just a minute. I will just ensure that this.
Please check, sir.
Okay.
Okay, please check.
Yes, now it's coming. Thank you. So just to ensure my slides are visible and voice quality is clear.
Yes, sir. Yes, lights are visible and voice is also clear.
Okay, good. So thanks a lot for all to join. And madam, I suppose it's till 2:30 we have to wind it up.
Yes, sir.
Okay, thank you. So now I will begin the technical discussion. So the topic which we want to discuss in this session is related to multimedia forensics and how the recent advances in machine learning and deep learning are leading this field. And the reason is very obvious that the question is seeing is still believing. So in good old days, when we used to have most of us are faculty in this session, so I guess almost all of us have used analog cameras, which used to have reel, and then we'll get it developed in a dark room, right? So those times when we used to have a picture, we used to quite easily believe it, that whatever is depicted in a picture or in a video recording, which used to be done on analog cassettes, they were quite believable. So, but nowadays, in the ages of digital multimedia and the enormous increase in the content, user-generated content particularly, which is available on the internet, thanks to the low-cost data, it's really most of the time actually we doubt when we see an image or a video. Our first question is not to by default believe it that it's true, but we actually disbelieve it. That whatever is shown in the picture is most likely not correct, or whatever is shown on a audio recording or a video recording is most likely manipulated. We first thought is of not believing, and after that, when then we may go on to see, okay, examine if the content is actually worth believing. So that's the central question we want to see how we can address. I am Nitin Khanna, and I am the principal coordinator for the lab, Multimedia Analysis and Security Lab at Indian Institute of Technology, Gandhinagar. The content of this slide is general content, which is in the field of multimedia forensics, as well as what the advances we have done in our lab. Okay, so oftentimes we keep the acknowledgement slide to the last, and then what happens at the end, we don't have time. So the acknowledgement slide is skipped. So I don't want to do that. So this content is a lot of generated by many of the members of the Manas lab, present and past, and as well as collaborators. Particularly two of my PhD students, Sharad Joshi and Vinay Verma, have done a lot of work in field of forensics. Sharad Joshi did a lot of work in printer forensics area, where he was dealing with hard copy printed documents, and Vinay Verma just finished with his work on images, particularly compression. So we'll go in detail of what we exactly see. And of course, this work is possible only because of the generous funding I have received for my lab from IIT Gandhinagar Startup Grant, as well as a Board of Research in Nuclear Sciences, BRNS, and Department of Science and Technology, DST. So now let's go into the technical content. Okay, for the technical content, I like to draw on the screen. So I will flip this into a tablet mode so that I can start drawing as well. Just a minute, I'm trying to figure out how to do that. Okay. So madam, I believe my screen is still visible clearly, right?
Yes, sir. It is visible. We can see some marker also on the side.
Sure. So let's look at this image. When you look at this image, this is an image which was sent around the world by France Press in some years back, and that was demonstration of the military capability of the nation, right? And when you look at this image, I am pretty sure because of all the transmission losses which are happening in this online medium, you cannot see any defect in this image, and it looks like a real nice image. So this is the kind of images or videos I am talking about. This discussion is not about the images which are like cartoonish kind of images or which are visibly different from real images. These are the images which are visibly as good as a actual camera captured images. So that on visual perception, it's very hard to detect. And even if it is possible to detect by visual analysis, if we zoom this image to a high degree, and let us see if I can zoom. If I zoom this image to a very high degree, it might be somewhat possible for someone to guess that there are some problems in this image. But even if those situations are possible, the other important point about the kind of multimedia we are discussing is the user-generated multimedia. That means these are not selected multimedia only by some publication houses or in limited quantity. So even if human analysis is possible, that's not feasible to do for all the tons of millions of images floating around and every day uploaded by the normal user. Okay, now looking at this image by default, it looks nice, but let's look at the actual image. So this was the actual image of the earlier image I have shown. So when we look at these two images side by side, then of course it's very easy for someone to figure out that this portion of the image, okay, this is drawing. Let me just fix the marker first. Okay, just give me 1 second. Okay, so it is obvious that this portion which I have highlighted, that portion is actually created falsely by the software and it's not present in the original image, right? So that's the kind of images that if you look at side by side we can identify, but in actual images it's not possible to identify those things, right? So what we do to address these kind of scenarios, and we have to keep in mind that we are referring to images for which original image is not available. So comparison of the two images is not an option. Second thing I like to highlight that these are the images for which we are not going to utilize some kind of watermarking or other signatures. Watermarking are signatures which are extensively embedded in an image at the time of generation. Because if you don't embed them at the time of generation, we are not sure that the image or any multimedia content, if it is already compromised, then embedding a watermark is not going to help us, right? So we want to do this for images without this original is not going to be available to us, neither there going to be any kind of watermark or anything else available to us for the embedding in the image. And there are lots of those images. I just picked up example. Here are the references. If you go to, there are a lot of those images. Now, one thing I would like to point out that it's not that these image forgeries are just new. Even in 80s, 60s, so with the beginning of the photography itself, people started manipulating images, right? That's kind of human nature, if you say. But the distinction is that at that time, when the images were very rare and the analog cameras were capturing them, the manipulation was not easy. So manipulating an image by, say, removing an object or adding another object in the image was a specialized art. Anyone can do it only if he or she has a specialization to work on that dark room on the films, and before developing the film, if you modify that silver halide screen and then do something. So that was very restricted art. So number of forgeries in the ages of analog time were very rare, first of all, and then secondly, even if they were made, they were not so sophisticated. So they're quite often easy to identify by looking at them. Perceptual identification was easy. This is not the case nowadays. Okay, so nowadays what is happening, that the amount of content, digital content online is very large and increasing day by day, and it's generated by common user, not sophisticated photographers, right? These are some of the numbers that in 2000 as of 2019, 1.36 lakh images, photos are uploaded per minute. So we can think of the enormity of data we are talking about. It's not possible to deal with such data by human inspection. Okay, so that's one side is this data, which is increasing day by day. Other side is now we have editing softwares which are easily available. So there's no darkroom requirement. There is no requirement of sophisticated skills. People can easily manipulate. And as day by day, you will see that even now the softwares for manipulation are quite lightweight. That lightweight in the sense they can run even on handheld devices. a tablet or a mobile phone, and you don't need even a sophisticated software or some software which will require very heavy processing time. So for example, processing something in Adobe Photoshop is going to be a little tricky because first of all, it's paid software, and then secondly, it may require little more computational resources to run. But editing an image in a simple app on a mobile phone, that's going to be quite easy. So both the things are there: increasing digital data, and secondly, easier to use softwares which are going to be used for manipulation of this digital data. So these two together are motivating us to address the problem where we want to address perceptually realistic forgeries. Okay. Another related field which I'm not going to address in this is the field of distinction of images or videos which are realistic or camera captured, or when you say natural images, versus the images which are generated by a computer. So computer generated images versus what you call natural scenes. So that's another field where we need distinction: multimedia source, what source it is coming from. And in that field, I think there was a session where there was a discussion about deepfakes, how deepfakes are nowadays generating really artificial content which looks very close to real content. Okay, so, and same thing, I'm not emphasizing about audio, but same thing holds for audio as well. Okay, so how we are going to address this scenario? That's our question. And these kind of questions become even more pertinent when we want to utilize this in the court of law for some specific evidence, or even from day-to-day transactions, especially nowadays when a lot of people are working from home. Now we do a lot of even signatures. Instead of signing on a hard copy, I'll just sign in using my tablet on a paper and submit to the required department, right? So that becomes more and more pertinent, how to take care of this digital multimedia. Okay, so now we want to develop a series of blind systems. Blind systems, I specified earlier that we are not going to have access to the original multimedia. Because why that is not going to be possible? Think about it. If we are going to be concerned about originality of only limited content, say only the mark sheets of all the students, or we are going to be concerned about only the passports or things like that. If the content is limited, there is a possibility that we can generate a centralized digital repository where we have authentic version of the original mark sheets of all the candidates which have graduated from our college, and then whenever their query comes, we can match with it, right? But what the kind of multimedia we were discussing today is user generated multimedia, for which there is no feasibility of creating a centralized repository. So we want to have blind systems without access to the original multimedia. And then we want to have a series of systems which will address this problem, because over the decades of research in this community, which has picked up recently last 10 years a lot, it's very clear for the forensic analyst that a single tool is not going to be applicable. So you have to address the problem from multiple angles. Okay. And the question with couple of primary questions we'll be asking is identifying the connection with the claim device. So a photographer has a photo captured, and he claims that this photo is captured using a particular camera. And now we want to link that, whether can I link this particular video or a photo or a audio to its source. So if it's a audio, we want to map it to a particular microphone which was used for recording. And if it's a video camera, I want to link the video camera to a particular video which we have available. So connection with the claim device. And then we also want to see whether the multimedia is depicting originally recorded event. That means it's not that after recording some manipulation was done. Okay. So we are going to utilize digital footprints in this scheme of systems we are going to design. Okay. So digital footprints can be at various levels. Footprints which are left at the acquisition time, when the image or audio is acquired. So I'll mostly talk about images in this discussion because of the restriction of time, but some of these techniques are easily generalizable to videos if we consider videos as a sequence of frames or images. And there are other research also which address one-dimensional signals or audios for that. Okay. And then, either during acquisition, we capture these footprints, or we relate the footprints which are left during the post-processing steps. And compression is, of course, all of us know, is very prominent in each of these systems, because without compression, it will not be possible to transmit the images or multimedia across the network with limited bandwidth and other restrictions. Okay, so we can divide the whole. Again, this is one way of looking at the division. There are other kinds of classification also possible. Okay, and oftentimes the tools which will be designed or systems which are designed are not incorporating only one kind of signatures. They will incorporate multiple of them in together. Okay, but to conceptually understand it in a easier way, let's think of acquisition-based footprints, coding-based footprints, and editing-based footprints. So coding, referring here, is the compression, either image compression or video compression, and acquisition at the time of acquiring the image. Okay. So what specific questions we can answer? Okay, so we are going to flag if the multimedia is potentially tampered. Okay. And then once that our system flags that it's potentially tampered, then we need to do further manual analysis. So that's the state of art of multimedia forensic systems which are present today, that none of them are going to give you 100% accurate and 100% precise location of forgery. But still they are very beneficial because they are going to give us a pre-filter, in the sense that instead of, now earlier we looked at one of the slides where like 1.5 lakhs images per minute. So now 1.5 lakhs images per minute uploaded on the internet, we don't have to go through all those images and verify. Instead of that, these tools will act as a pre-filtering mechanism, and we can indicate that out of those potentially X number of images are likely to be tampered, then those particular images and which are utilized for specific applications can be tagged as potentially forged. So that's the idea. Now, then other this thing is about, so that previous discussion was about images and videos, this content which is originally digital in nature. Then other content which we often use is, to begin with, is analog in nature, in the sense that it's a printed document. So printed document by design, it's analog in nature, and then we use them in a digital manner. So for example, printed document, we take picture of the document and transmit it using some application or email it to each other, things like that. And once it comes to the digital form, then again making forgeries or tampering the content becomes very easy. So that's the other kind of digital content we are going to be concerned about, which is converted to digital form by scanning or taking photo of a digital document. And we have seen across the news, only few of them are listed here, that how these kind of things, for example, this there was some time back a CBSE paper leak. So what someone did was took pictures of the printed exam papers and transmitted it over to some other people, right? So now once this is transmitted, we want to track back that, okay, this particular digital image of the exam paper which is transmitted, from which camera it originated, can we trace back? So that's one way to track the person who has done this. So, and that's what we talk about in multimedia forensics, because we will not discuss something. So I will point out there another field called computer forensics, or you will often refer to as network forensics and some other names, where you will try to trace the original data or what tampering it has done or from where it is originated, based on either networking characteristics or like what's the IP address it has followed, from which IP address it has originated from, then it went to which IP and things like that. So that's a different field. That's in the area of network forensics. Then in computer forensics, there are other field where we try to recover the digital multimedia after it has been deleted on a hard drive or things like that. That's also another field which will be mainly referred as computer forensics. But what we are referring here is multimedia forensics, forensics specific to the multimedia without utilizing other side information. So that's why I told in the beginning that all these are going to be a set of tools that are going to work together. Okay, so let's set up the problem first, understand what kind of things we are going to planning to address, and then we will see how we can utilize machine learning and deep learning to do that. Okay, so there are a lot of things going around which are related to forging of documents. Okay, so document forgery is another field which need immediate attention. Okay, so now let's zoom down to specific term, multimedia forensics. So we are referring to ascertaining origin and processing history of a multimedia file. So it can be printed document, it can be image, it can be video. And among those, there are many forensics tasks. Source ID identification is important. So what I mean by source ID identification, given any kind of content, we want to trace it back or connect it with the sensor which was used to produce it. So for example, if it is a printed document, we like to connect it to a particular printer which was used to print it. If it is an image, a particular camera. Now within that also there are multiple levels of problems. For example, we may want to connect an image to a specific camera, or say, think of cell phone camera, the cell phone with a specific IMEI number, a specific number, right? That one level of very fine level of connection. One bigger level might be, instead of interested in a specific instance of the cell phone camera, we want to connect it which brand and model camera it was. So it was Samsung Galaxy XYZ, something like that, right? So that's another level. Another level, maybe we want to say, okay, this is either a Samsung camera or a, say, Sony or something, right? And these kind of hierarchical classification, why they become possible? Because there are certain signatures which remain same. So although each and every device, say Samsung Galaxy XYZ, each and every instance of that will have a camera. This camera is used to capture images, right? So across all the devices of this particular make and model, the cameras will be of same specification, right? So although there will be certain differences in from one camera to another, that's why that kind of differences will arise, because in the manufacturing process, we don't want to make exact replica of to very great precision. We only want to make devices that can be called exact replica as long as the user is going to see it as that way. What I mean by that is that, say, number of a 10 megapixel camera. So two 10 megapixel camera or exact same brand and model, they'll both of them generate images of 10 megapixel. That's all we want. And the specification of those images will be very similar. But some of the artifacts or some of the defects which remain at the sensor level, these cameras either use a CCD sensor or a CMOS sensor, which remain at the sensor level, that we are not so concerned about eliminating as long as they are visually same. So they are not so in every device or sensor which a manufacturer designs and sells into the market, they are only concerned about eliminating perceptual differences. So perceptually all those images look same. But when we analyze with the help of, that's where now the machine learning and data driven learning and deep learning is going to come in picture, that we are going to focus on the artifacts or focus on the differences in the images which are not visible to the common eye. But if we see it, for example, it's a printed document. If we scan it at a very high resolution, say I scan a printed document at 1200 dpi, 1200 dots per inch. So in every inch you have 1200 pixels. So if I scan a document at that high resolution, I will be able to see differences from one printer to another. While from a common person's perspective, if you just look at a printout on a A4 sheet, two printers of the same make and model will give almost same quality of the printout, as long as the toner level is fixed. So we are not talking about one printer having a very low ink cartridge, another printer is having a new ink cartridge. If the toner level is same, their output will visually look same. So that is the whole idea, that manufacturers are minimizing the artifacts or any kind of deficiencies in the sensor, as long as they are perceptually evident. But once they are below that perceptual threshold, there is no need to minimize that. And that's where this whole field tries to utilize those imperceptual defects or artifacts to connect the source to its generated output. Okay. And once we do that, we can address a number of problems. We can address problems to do copyright infringement. So infringement of a photographer's original photo. You take a photograph from your camera and you post it for a competition, and you win that competition. Someone else downloads that and you tries to use it his or her authentic image. How do we prove that that's not from? So then if I can design an algorithm which will link that particular photograph to a specific camera which this original photographer has used, then I can claim that it's his or her copyright. Similarly, ownership attribution, in this case, the owner presents this thing that yes, this belongs to me, now connect it, right? And then leak identification, if certain sensitive information is leaked in a chain of custody, then you can identify the person who is responsible for leaking that information. Okay, now let's go to a specific. So that was the general idea. I'll pause for a second and see if there are any questions posted. Not yet. Okay. So now let's go to a specific thing, which is coding weight based footprints, or as I told earlier, compression. So now most of us, whatever cameras we use, actually they capture images in JPEG format. JPEG is an image compression standard, de facto present in almost every device which relates to images. JPEG 2000 is another upcoming one, but still not so commercially available in all the devices. So JPEG is still the prominent one. So all these now are JPEG format images. So what within JPEG format also, now you will see that if you acquire the same scene from two different devices, the size of the image file is going to be different. Or even from your own camera, there are options that you can change the low quality, high quality, medium quality image, and then you can acquire it. And then we acquire the image and say we transmit it on a social media platform. So as soon as you upload it on a social media platform, most of the social media platforms are actually going to recompress it or compress it again to decrease the size of the image. Right? So this JPEG is very prevalent of doing that. Okay. So there was a study conducted in 2018 where they collected a lot of images over the span of 2 years, and they analyzed it, how many of them are JPEG images, how many of them are authentic images, how many are not authentic images. Okay. So they came back with the number that around 78% of these images are JPEG format. So a vast majority is JPEG images. Okay. Then within the JPEG images, we'll go into more detail just in a few minutes. A central part of the JPEG compression is what we call Q matrix or quantization matrix. Okay. So there are not a single quantization matrix, but a large number of quantization matrices which any JPEG compression algorithm can utilize. Okay. And then there are standard quantization matrices which are depicted in the JPEG compression standard. 100 of them are, when the JPEG standard was defined, they along with that described that these 100 options of quantization matrices are there. If you want to compress with say reduce the file size more at the cost of image not looking so good, then you can use one kind of quantization matrix. If you want a high quality image, we want another quantization matrix. So high quality image will have larger file size, but quality of the image will also be good. Why will someone want to do that, reduce the quality? Because that depends on what the application is, right? In many of the applications, when we are posting images on web, actually we don't need that high quality images, high quality in the sense how many number of pixels that image should have, right? Because most of the display devices, if people are viewing a handheld device, are going to be limited to say 1000 by 2000 pixels or something like that. So they're not going to have 80 megapixel in the display device, right? So if the image is only for display, and then because of the limitation on the internet also, people like to view it on a downsampled scale, right? So that's one scenario where someone like to compress it more. The other extreme is that suppose the image is acquired for later on printing using a color printer. And in that scenario, we like a high quality image. So that's why, although the name is a single JPEG, but there are wide variety of possibilities to use, which decide the trade-off between amount of compression and the quality of the image. And a lot of those Q matrices are going to be non-standard. Okay. Okay, so now let's dive a little deep into how the JPEG compression works. Okay, now why this thing is important? So within this discussion today, I'm going to talk about both the sides. So machine learning, where learning is on a set of features. So these terms, I think learning, features, training, testing, all that is clear from all the discussions till now. So I'm not going to details of them. So one class of algorithms are what we call feature engineering based or feature based, where we design handcrafted features or features which are based on some understanding of the physics or science behind the problem, right? That's one extreme. So when we design the features, then we feed these features into some machine learning algorithm, say support vector machine, or if you want to do unsupervised learning, we feed into some clustering algorithms, say k-means clustering, generalized k-means clustering, so on and so forth, right? Or spectral clustering. So first step is feature engineering, designing a feature, and second step is then feeding into a suitable clustering algorithm or a classifier, right? Like a support vector machine. That's one X. The other side is that we don't worry about the physics or science behind the system itself, and we just deal with the data. That I have the data, I have thousands of images. Now I want to figure out which camera this image has come from. So that's the domain when we go to deep learning. That we don't do feature engineering, we don't do handcrafted features, and then we just rely on the data to design a system. A number of systems will try to utilize both of these. That okay, you feed into the knowledge of the system, physical knowledge of the system, and how the data is generated, and then after that level, then you apply some kind of deep learning algorithm, or you use the deep learning algorithms to extract those features, and just before the fully connected layer or a few layers back, we try to see what the interpretation of these features are, right? So we will see both the ideas, that where we will design features based on understanding of the system, and then where we will blindly use the data to learn the features themselves. Both have their own advantages. One of the very key advantages of designing the feature-based systems or designing the features themselves appropriately is that since we are utilizing the physics or science of the system, we can do with much lesser training data. Okay. While if you want to learn everything from the data itself, you will require much larger training data. So that's one. So a number of problems where training data is limited, we will go with feature engineering or handcrafted features. And after that, on top of that, we'll try to utilize the machine learning algorithm. Okay. So to do this JPEG compression based forensics, let's get a basic idea of how the JPEG compression works. Okay. So we have a image. This is our input image I. Say a 10 megapixel image which you have acquired from your camera. So before the image is saved into the camera, it is saved into the camera as a JPEG file. So these are the three main steps which go into this. First is dividing the image into 8x8 small blocks and performing what we call DCT or discrete cosine transform on that. Second step is that we'll do quantization. Quantization basically to reduce the information or number of bits needed to save a particular pixel value, and then we do entropy encoding. Okay, entropy encoding And in the reverse, when I have a JPEG file, I want to get my output. What is my output image? I am going to reverse it. So I'll do entropy encoding. Reverse of that, I'm going to do entropy decoding. Then I'll do dequantization. In the dequantization step, I'll need also what the quantization matrix was used earlier for quantization. Then I'll do inverse discrete cosine transformation, again on 8x8 level, and there is rounding and truncation operation involved. Then I'll get finally my original image which was there. Okay, it's written as I dash because it's approximation to the original image. In this whole thing, these two operations, entropy encoding and entropy decoding, they are perfectly lossless, or they do what we get basically at this point, whatever is fed, we get back at this point. Okay. From here to here, there is some transmission, or there may be storage, and that might lead to some loss. We are not considering that loss. So we are assuming that the same file J which was transmitted is received over here. Because I mentioned earlier, that will come into the part of network forensics. If we want to utilize, okay, if some of the bits in the image file is corrupted, then what can we decipher from there and things like that, right? So we are assuming that there is no loss in transmission. We get back the same JPEG file. Now from the same JPEG file, this entropy decoding is performed. So encoding and decoding are just opposite to each other. There are no losses. So we can skip that operation when we're designing a system. Now the key thing which leads to losses is this pair of quantization and dequantization. So F over Q, F is the forward, after forward DCT transform, what I have got coefficient, those are represented as F. Q is the quantization matrix. So these are done at 8x8 DCT level, right? So they are not on each number, but actually they are done at matrix level. Okay. So each the 8x8 matrix is processed at once. So quantization, this Q is also a matrix. That's why this belongs to n natural numbers, a space of natural numbers 8x8. So 64 dimensional space is where this Q matrix is going to stay. Okay, and these are matrix operations. So you're dividing one matrix by another. So how we are going to divide one matrix by another? In this case, these are what we call element wise operations. So we are not taking 1 over Q does not mean Q inverse in the sense of matrix inversion. F over Q is, that means every location of F, say F1, 1 is divided by Q1, 1. So that's called element by element operation. And same way, this multiplication by Q, again, that multiplication is element by element multiplication. Okay. The details of that, why those particular way, those are in JPEG design of JPEG standards. Some other time we can go into detail of that. But for now, let's see that this is what it takes to do this JPEG compression. Okay. Now, let's see where this problem is going to come. So when you want to manipulate, we want to open an image and we want to say change brightness or change the face color or change the background from one color to another. So what we are going to do, we have to open the image and see it in the spatial domain. That's how we will see the image. When we are seeing the spatial domain. But actually it is relying on the computer in the compressed JPEG file. So we have to open it in the spatial domain, and for that all this decompression operation will be done. And then what we do, adversary is going to open this image and change something. So suppose this denotes the change region, manipulated region is denoted by this. Now after manipulation, it has to go back as a JPEG file. So again a compression operation has to happen, because the file will be transmitted or stored only in the JPEG file. Spatial domain only for visualization. So now from this JPEG file, I have got to this JPEG file. And what our target is that this forged JPEG file, can we identify that this is forged? That means some particular portion here was manipulated, and then further step, can we identify which portion was manipulated? So that's the overall plan. Now what you'll see that this region, region highlighted in a particular color, has undergone compression in a different way compared to this region, which are not highlighted. right? So that's the kind of footprints we are going to utilize. So this grid is shown here. This grid is shown to indicate that 8x8 blocks, each of the 8x8 blocks we're talking about. So some of these blocks will go single compression, while others will go double compression, because this thing which is manipulated, what will happen when you're in that region? So that region is a manipulated region. So either that region might have come from some other image. We have taken face from one image and we have put it here. Like in the earlier missile example, we saw that one missile was taken from one place and copy and pasted in the same image. So instead of 3 or 4, it was showing one more missile, right? So that region has come from some other place and then pasted here. So when it comes from some other place and pasted here, it's very likely that the digital footprints corresponding to compression is going to get lost. So this outer area, which is not highlighted, will get double compressed with proper aligned, while this inner area will be, which is manipulated, will be single compressed. So now within a same image, we have got, so I took one example. There are other possibility also, that one may be double compressed, another may be triple compressed, right? So number of compressions those particular area or those particular blocks have undergone, they vary. Some of them might be n number of compression in general, and some other maybe n plus 1 number of compression. So that's the basic idea, that we want to detect how many compressions a particular part of the image has undergone. Okay, and if we can design those algorithms, it will be useful. Now let's go how we are going to do this. So setting up a problem in any research is very important to understand what kind of tools. I will skip the mathematics of this, maybe pick up in question answer if you want. So now the same thing is depicted what I was saying. If it is aligned or compressed twice, then basically what will happen, the first compression we divide by Q1, then when we recompress, we are going to multiply by Q1 back. And then once we compress again, we are going to divide by some other Q2. So this is this portion when it is undergone twice the compression. This is the blocks which have gone only single compression, okay, by the second time when you compress. So we want to differentiate between these kind of blocks. Okay, so now why I was going through that, so one thing was just to take this blindly and put into a classifier and try to train it. Other is try to utilize the, now we have understood that what is happening is either a Q1 by Q2 kind of this thing when we double compress, or just division by Q2. So what we do, we look at the histogram of these images. Okay, we look at, okay, if this is compressed twice with Q1 is equal to 3, Q2 is equal to 2, then how the histogram will look like. And then another histogram after recompression, right? Or actually decompression. When it decompress, then we have multiplied by Q1. Okay. So once, now this is the central part. What is happening? Once we have divided by Q1, then multiplied by Q1 again, and divide by Q2, we'll observe that there are gaps in the histogram bins. Earlier, it was all continuous. All the bins were populated, or every value was occurring. But now, in the compressed coefficients, you'll see some values are missing. So this particular example was taken with specific values of Q1 and Q2, where the gaps are very evident. Some other values, combination of Q1, Q2, gaps may not be visually evident as it is there. Again, this is visual evidence is there in the some other feature domain, histogram domain, which you are seeing. Not the image itself doesn't give any visual artifact. Okay, so that's one level of artifact we are seeing we can utilize. Okay. So then different values of Q1, Q2 will give us different level of visualization. So now what we do is we are utilizing that this all the points which are indicated in green are going to be, so remember processing is happening at 8x8 level. So that means all the top corners of the 8x8 block are quantized with the same number. Or in other words, we know that these, all the green ones have some similar characteristic versus the other colors have. That's where now the physics of the problem is coming into picture. If we would not have considered all the JPEG background, what we have done, what we would have done to train this system, we would have put this entire block or this entire image as a single entity in my CNN or any other kind of learning system. We would have not incorporated that. Actually, I know already that all these top corner blocks or all these top corner pixels have some specific characteristic which is distinct from these other colors. So instead of now feeding this whole thing into a single system or single learning system, what I can design a feature based on these, all these blocks together, and then these color blocks separately. That's one way. Either I design features based on this, or what I do, I train 3 different learning systems. So I train one learning system for this, another second one for this, and third one for this. Because now I know my data is different, like they are following different characteristics. So that's where understanding the background is important. Now, once we have understood that idea, I will go through this quickly, and we'll take some of the question answer session. So then we are designing a feature in this space, which is coming from each of those blocks. So there's 8x8 blocks were there. So that's why this 64 dimension, 64 histograms will come, and 2b plus 1, depending on what is the number of bins I am seeing, minus b to plus b, if I am taking. So 2b plus 1 total number of bins will come. And 2, because what we are doing, we are also appending the quantization number by which it was Q1, Q2, which I was referring earlier. I know what is my last quantization, so I can utilize it. So remember that JPEG image, when you are saving, actually it stores the quantization matrix, which was used to compress it, because at the time of decompression, whenever we need to see the image in a special domain, I need that quantization matrix. So that quantization matrix Q is saved, but Q is only saved for the second or final quantization. Okay, because the previous ones are lost. So whenever you save a JPEG image, you only save the latest quantization matrix which you needed to decompress it. Okay, so we utilize that information as well, and then in this feature vector. Okay, then we need to do this on a large size data set of what we're doing is single compressed and double compressed patches. So some of the patches are single compressed, some of the patches are double compressed, and then we are utilizing large number of Q matrices. So it's not just, remember I told that there are standard 100 Q matrices that are standard, but we are utilizing much larger than that set because a lot more possibilities exist. Okay, and from different camera models. So in this problem, the intention is not to differentiate which camera model the image is coming from, but which compression is performed by which quality factor. That's what the goal is, right? So, and a specific thing we are doing is Q1 not equal to Q2. That means the first compression and second compression are performed as different quality. So in terms of a normal user, what you can think of, the first image was saved as say high quality, and a second one you edited it and saved in Photoshop. Even if you choose high quality of Photoshop and high quality of your own cell phone camera is going to be very likely different, right? So that's why now the two quantization matrices we are considering as different. And then here is the kind of results we have obtained. Okay, so I guess true positive rate and true negative rate, these terminologies already discussed, so I'll not go into detail. A standard terminology for evaluating machine learning systems, and then the test accuracy. Okay, so we can see that the proposed system which we designed in our lab is giving much better test accuracy and is so, and the success of the system is why? Because we have designed features in taking into account the process by which the JPEG compressed image was generated. Okay, there are some more results. So we also experimented with the small patches. Okay, instead of, now think of compared to the normal images what we used, 10 megapixel image is a normal image, or 5 megapixel is a normal camera available in most of the mobile phones. These are pretty small patches. So if I can, so what this algorithm is basically saying, that given a patch of size 64 cross 64, I can tell with 88% accuracy whether that's a single compressed patch or double compressed patch. So now if in a given image, we can identify that some of the patches are coming out to be single compressed, while some of the patches are coming out to be double compressed. We know that this is a mixture of the compression. That means this image is very likely to be tampered. Okay. And the other is that, okay, these are small patches. So if I want to take the decision of the whole image, I can do majority voting to find out the whole image, whether the image was single compressed or double compressed. The image level accuracy will be much larger than this, because then when we do majority voting, is going to improve. Okay, so that's one. Then another interesting area is when you have unseen quantization matrix. That means you don't know, because we used 1100 some quantization matrices, but that's also not a closed set. There may be much larger number of quantization tables, right? So it's also important to design systems which will uh, be successful even when the training data is coming from a different quantization matrix. First quantization matrix I'm talking about, because the second or final quantization matrix is anyway known, embedded in the EXIF information of the JPEG. It's the first quantization matrix which is not known. Okay, so this is also an important scenario, and you can see that it's still not 100%. So there are scopes of improvement. So this is a very upcoming field which has a lot of scope of research and improvement, and so many of us will find it very interesting to do some research on. Okay, then this slide shows that how we can utilize the algorithm which we have just discussed, that system, to find out the forgery. So this ground truth GT is indicating the forged region in the image. This is the tampered image corresponding to this original image. So some particular region was forged, and we can see that this proposed one is getting it pretty correctly. There are some false alarms. So there are some regions which are which algorithm says they are forged, but actually they are not forged. So those are scopes of improvement, but overall you can see that this is very good. So we can identify these small patches. And again, remember that what is happening, if we look at these images just on themselves, visually they are not having any artifact, okay, that you can easily identify that this patch is wrong. Visually it looks okay. Okay, but when we run the algorithm, then we can see that yes, there are forgeries. Okay, so that's one problem where we have utilized this creation of particular features, and then we have, okay, we'll skip these. So this is what I was saying. If the detection says that we have more than one number of compression, while the person giving me image told it's the original image. If it is original JPEG image without any manipulation, then it should be only single compression. But if some of the patches come out to be not singly compressed, then we can say that there are possibility of manipulation. Okay. So that's what I was saying, that we are going to utilize a CNN, convolutional neural network. But before that convolutional neural network, we are going to design these features appropriately. Instead of feeding the image directly to CNN, we first do all the processing, generate these kind of features, and then we feed into the CNN. And then once we have done it at each and every block, that's what this thing is showing, division into block, we can combine them using majority voting to get the level of the complete data. Okay. So these are details of the histogram generation process and other things, which we will skip. Now, the other problem, the first problem which I showed the result, was single versus double compression. This is when we have more than one compression. So C1 denotes the images which are compressed once, C2 double compressed, C3 triple compressed, C4 4 time compressed. Now, why these many? Why we need to address that? Because think about it, I just told that most of these images are going to be transmitted over some social media, right? That's what we do, or we post it online on Facebook or something like that. So whenever we are doing that, the social media itself is going to do one compression. So original image captured into the camera, it's compressed once. I open it, I change some region, some part of it, or maybe just change the brightness. I save it again, compress twice, so 2 compressions done. And then when I upload into, say, send it to my friend using WhatsApp, I have compressed it thrice. So 3 compressions done. By the time the image reaches my friend, it is compressed thrice, and one of those compressions corresponded to my changing the brightness, while the other compression is bound to happen because I am sending over WhatsApp, right? So that's why more than one compressions are also an important thing to address. Okay. I'm just seeing. Okay. So I have 20 more minutes left, so I want to go into some of those printed documents things as well. So I will skip. Okay, just look at some of the results. So now these images show the result that again we are identifying at block level. So just to keep in mind my original point that none of these systems are going to give us 100% accuracy. The present state of art, none of the SOTA methods is 100%. Okay, so these are some false alarms that this green patch is indicating that this belongs to some other compression, while it is actually a single compressed image. So like that, there are some false alarms are there. Okay. Now, the next thing which we skipped was we took the scenario of only when the first compression and second compression were of different quantization metrics. That this scenario now is when they are the same quantization metrics. So when they are of the same quantization metrics, that means first think of a simple term. We divided say by 2 while compressing it at first level in the quantization step. Then in dequantization, we are going to multiply by 2. But because of this square brackets which are indicating rounding operation, they are not invertible. So this Q1, so this is also Q1 over here, right? But this operation is not going to get cancelled because of the rounding and truncation error which are going to occur. Okay. So Q1 and Q2 case need to be dealt separately, because the kind of artifacts which were present in Q1 not equal to Q2, that's not going to be similar in a Q1 is equal to Q2 scenario. So some other footprints need to be designed, and we are going to focus on rounding and truncation errors. So we can skip these, go on through that. So one key aspect here to emphasize is the idea of stability index. Now, since we are compressing by the same factor, same quality factor, or same high compression or low compression, or same quantization value, what will happen after first or second or third compression, the image or the blocks are very likely to become same. That means there will be no further change. While if the quality factors are different, Q1 not equal to Q2, then this is very less likely to happen. So we define a term, stability index, that indicates after how many compressions the blocks become exactly same. There is no further change if you keep on compressing them again. So this idea is utilized. Okay, skip the details. Okay, yeah, so just focus on this thing. So now we can see this is result on 8x8 blocks, very small blocks we are talking about. And when the quality factor is low quality factor means very high compression, and high quality factor means low compression or larger file size. So when the quality factors is low, then my accuracy or performance of the algorithm TPR, TN in terms of TPR, TNR is not that great as compared to when high compression. But that's not so worrisome, because we hardly use such low compression in our actual day-to-day image transmission. Because when you apply very low compression like that of value 20, your image will perceptually start looking bad. So we don't want to compress it to such a small degree that you lose the information present in the image, or image looks visually bad. So most of the time the compression used is around 80 and 85 in that region rather than the region of 20. So in that usable range, we are saying that mostly we are getting good accuracy. So that's about JPEG images and compression. Now, other thing I told, security of the documents. So now, security of the documents, we wanted, one problem is to identify the source printer of the document. So we have n number of printers, P1 to Pn. Some document is printed, and at the end, we have this test document. And I want to identify what is this XPX, what is this unknown printer which was used to print that document. Okay, so we'll again design machine learning based algorithm, because visual perception, visual inspection is not going to be useful. Then there are other methods to solve this problem where people will do chemical analysis of the ink of the document, right? But many of those things, almost all of them are very time consuming and they need specific skills. But many of them are actually intrusive also, in the sense that in the process of removing the ink from the page and then analyzing it in the lab, you're going to destroy the document itself, right? So many of them are destructive. So, but we want digital techniques which will be easy to operate, and which will require not sophisticated equipment rather than just a reference scanner. This reference scanner is just a normal desktop scanner, flatbed scanner, which most of us use in our offices, not a sophisticated spectrometer or something to analyze the ink, right? And then it should be non-destructible. Once we scan, we are only going to process these scanned documents, and I am not destroying the original printed document that's left as such. Okay, and I want to answer the question that given this document, I find out which printer it is coming from. Okay, so that's the problem statement. Again, our target is common source printers which are low cost and which are not having any sophisticated security mechanism. So these kind of documents, we are not talking about currency notes, passport, so on and so forth, because they are printed by specialized hardware, specialized printers, and there are security mechanisms embedded in them. We are talking about securing the documents which are printed by a printer in our office, or and you get a photocopy done in 1 or 2 rupees. Those photocopiers are not going to be equipped with any sophisticated markings, right? So the kind of so emphasis again on user generated content. Okay, and we are not going to depth of how these environmental conditions are going to impact the system. We are assuming normal environment conditions and operations, and then we try to address this. Okay, let's see. So I already told about why we want to have digital methods. This part again, I already explained that there is extrinsic signature, there are intrinsic signatures. Intrinsic, which you add explicitly to a document or an image. Intrinsic, which are there present in the sensor data itself. Okay. We are going to talk about intrinsic one only. That means we are not going to change anything in the printing mechanism. Now let's see that probably in your screen, because of this transmission, there is some reduction in image quality, so you may not be able to see, but something might be visible, that if you look at this, so same character printed by different printers, you can see that quality of the character is slightly varying. This is at very high zoom level. We don't see at this level in normal day-to-day uses. So one thing to observe is that it's not perfectly black. What we visually see, it's perfectly black and white. It's not perfectly black and white. There are some levels which are not neither perfectly black nor perfectly white. Those are because of the ink spread or the unaffected by paper quality and so on and so forth. So the key idea is that if we design machine vision systems which are going to utilize a high resolution scan of this thing, it will be better. So I'll skip the details. There are a lot of research done in this area. And different people propose different approaches based on utilizing any specific character. For example, a lot of research focused on character E. Why? Because E is the most frequently occurring character in English language. So there are high possibility of finding a E on a piece of paper. and then analyze that E and detect that what printer that was used to print it. So you see that all these 5 are printed by the same Canon printers only, but 5 different kind of Canon printers. Their make and model is different. Okay. So their visual quality looks, if you look at this edge thickness over here, say they are different. So, but now we don't want to design the features themselves. We want our system to learn. So, okay. So this is the overview of the system, that we are going to do what we call connected component analysis. So we are going to divide the whole scanned image into each connected component, and then each connected component is processed. Now we are emphasizing that this is just connected components. We are not doing what we call optical character recognition, or that we don't want to identify each and every character. Like some of the earlier methods, they are designed for a particular character, say E. Then you have to do OCR to find out where the E is occurring. Because again, you cannot do manually identify E, right? It's a huge volume data we are processing. Okay, so we work on all the characters. So a system is designed which can, let's say the name, texture-based single classifier method. So we are designing a single classifier which will work for all the characters. Okay, so that way we get rid of the need for applying a OCR. And then we do all this up till this point is basically feature extraction, what I was saying. So I've given you a flavor of a number of systems which do different kinds of feature extraction depending on what the source of data is and what kind of information you want to extract. And then a standard machine learning classifier, SVM, is what is used here. Okay, and then that gives us final identification results. Okay, so this is this one is a typical machine learning approach using SVM, where handcrafted features are used. And let's skip for these. Interest of time, we will skip these details. And I want to show you another system, which is a CNN based system. One advantage I pointed out earlier, that in the feature engineering approach, where we are designing a feature which are connected to some way to the actual system, what happens, the features themselves have some interpretation. So when you what is done here is 2 features are plotted, 2 more prominent features. So you can see that actually these each of the color correspond to a different printer. So you can see in this 2-dimensional space, actually 2 printers are separate, right? So the better a feature design is, the better separation will observe here in a smaller dimensional space. So that's one way to see. LDA is linear discriminant analysis. One strategy for feature reduction, and I'm not going to tell mathematics of it, that we can do if the time is there. And this is a description of the data set, that how we captured from different data set. And here are the accuracies, that 96% accuracy was obtained for classifying these printers. These printers, number of printers were 10 printers were taken, and a number of different manufacturing system. Okay. Then these are further analysis. One important study was what happens if we change the scan resolution, because if we are scanning at high resolutions, at 600 dpi, we are likely to get more information, but the trade-off is that now the images will be much larger, the processing time will be larger, and even scan time is going to be larger. And if this is going to be a system which needs to be deployed on internet, say we want to design a website where you forensics and where you post the forensic tool on a web server, and then anyone can upload their image, and then the web server does the analysis and sends back the result. Then utilizing a very high resolution image will be problematic, because transmission time will be larger, so on and so forth. So impact of resolution was important to analyze, and it turned out that even at smaller resolution, the system does very well. And then impact of different fonts. Okay, because one strategy is that you can always design a different SVM classifier. So over here, remember that when we are designing this SVM classifier, we can design a different classifier for different font. Train data we can vary. We can take train data of a particular font and design. As you know, any machine learning system is as good as the quality of train data you're going to supply to it. So training data I can vary, and then depending on the train data, I can get different classifiers. But that is going to be time consuming, that designing for every classifier. And moreover, amount of train data is important. How many pages, test pages we are going to print, train pages we are going to print from the same printer and analyze. So because of all these reasons, it's good that if a single system can be designed for different fonts. So this experiment just says that the features which are designed, they are good, they capture for all fonts, they capture different thing, but they're trained on different font differently. And this particular experiment shows that this printer 9, 10, and 11 are actually printers of same brand and model. So that means HP something of same brand and model, 3 different. So we buy 2 printers together of the same brand and model. In this case, 3 printers, we can still differentiate with a good accuracy. These are for classifying pages. So page level classification, we can get good accuracy. So that's this thing. And then the last we'll talk about, okay, this will skip, I think there is one. These are all specific feature engineering and then putting into machine learning system. Instead of that, let's just last 5 minutes. Are there any questions posted, Dr. Neelam?
Yes, sir. I can't see any questions posted till now.
Okay.
No questions on any board, neither on YouTube nor over here.
Okay, so we'll continue then. All these are different systems, so we'll skip them. Just wanted to show a deep learning based system just for completeness, that how. Okay, yeah. So this is a CNN, convolutional neural network based architecture for a smartphone based identification. So these are source printer identification system for text documents, but these are captured using phone instead of scanners. So we have a convolutional layer, which is followed by batch normalization and ReLU activation function. Then there is max pooling. So remember, these images are pretty small, 30 cross 30 patches. And we designed a 2-channel input image which are feeding. This is followed by another convolutional layer and max pooling. Then we flatten it, and then we are going to put in into a fully connected layer. So number of convolution layer right now in this, we are only showing 2 layers because the input size we have kept very small. But if you want to increase the depth of the network, we can further increase the depth of the network to get variety of other architecture and what kind of results we will get. Okay, so 3 more minutes. In 3 minutes, I think we should just look at the result. So this is important result to note, that by varying different patch sizes, the input to the network which we have shown earlier, we are getting consistently high accuracy. Okay. I think we will skip here. I will stop here with this result. Just go to the last slide. There's some references I have pointed out. We refer to go back and look at more details in these papers. This year, there are a lot of systems being proposed in recent times to address these kind of problems. So audience will like to go to the references. I think that's all. We'll finish here. 1 minute is left to be on time.
Any queries from anyone? I don't see any queries, so, but yeah. So thanks a lot, sir, for this wonderful session. You have talked about a very different perspective of research area, which we were not knowing much about, and we got the knowledge about that particular area and how machine learning can be used in this particular area. So thanks a lot for this wonderful session.
Thank you, madam. Thanks to all the participants for patiently hearing. There is a lot in research. We can go deep and deep, but
Yeah,
yes.
I know. So
Thanks.
there is some message from the chatbot that explanation was too deep and very clear, and thanks for that. That is what message we are getting on the chatbot. Even we are getting a lot of messages on the YouTube channel about session, positive feedbacks about the session. Thank you very much, sir, for this wonderful session. I'm really thankful for you to take out time and give a session for us, and uh, we always look forward to have you on our organization whenever the conditions allow us to do that. Thank you very much, sir.
Thank you, Rich madam. I will disconnect. Thanks a lot. I'll move on to my next thing. Thank you.
Okay, thank you.